Okay, good day to everybody. Okay, so for today chapters is that chapter 7 is about the instruction representation. For this chapter, I would explain the representation of the three formats of instruction machine language, which is R, I, and J. So before that, um, uh, I would briefly explain about the levels of representation. So when you try to write your program, okay, you will be writing the high level language, which is maybe C++ or Java. Okay, and then for example, this type of command or code, temp is equal to v array v index k, and then vk is equal to vk plus 1, and then vk plus 1 is equal to temp, which is like this is a swap technique. And then okay, we compile the code, okay, into an assembly language program such as MIPS in this case. Okay, so the code will be translated into this assembly language, and after that it will go to the assembler, okay, and transform or encode into a machine language program which consists of binary numbers. Okay, so after that, okay, it will be um, the machine language will be executed into the hardware block diagram, okay, such as the register file or ALU, and at the end of it, okay, the execution is through the implementation of the logic circuit diagram. Okay, so this will be the overall picture of how the program or instruction or the code will be executed inside the CPU. But our focus will be on this circle here, okay, whereby you will write the assembly language and then learn how they are assembled into the machine language. Okay, so um, so this would be the overview of what will be explained later on. Okay, so I would explain about the stock program, okay, idea, and then how the instruction is encoded into numbers, and then the method of encoding, okay, for types of R, I, and G format. Okay, so for the stock program concept, the computer is built on the two principles. One is the instructions are represented as a bit patterns. You can think of these patterns as numbers. Okay, so know that computer only understands 0 and 1. Okay, um, although we can understand numbers from 0 until 9 like a decimal, but the computer can only operate for 0 and 1 for on and off, um, high and low, okay, because of the construct of the computer itself is based on the electronic signals. So therefore, since these numbers, okay, since the instruction can be represented as the numbers, so the entire program can be stored in the memory to be read or written just like data. Okay, so to it will simplify, okay, the software and hardware of the computer system, as the memory technology for data is also used for the programs. Okay, by since that all instructions and data are stored in the memory, so everything has a memory address, such as the instructions, data. Okay, so all of this is are stored or accessed in words. Okay, so both branches and jumps also use the memory address. The C pointers, the C pointers that you have learned also use the memory address, as they can point to anything in memory. But unconstrained use of addresses can lead to nasty bugs. Okay, so usage of the pointers or memory address must be limited, as we have a limited registers, right? Okay, for C, it is up to you, okay, to determine the usage of the address. Whereas in the Java, they have some limitation. Okay, they limits the usage of these addresses. So one register would keep address of instruction being executed, which we call the program counter in the MIPS code. Okay, so basically a pointer to memory, where Intel call its instruction address pointer as the meta name. Okay, but actually, most of the most of the assembly language use this program counter. Okay, as common name on the pointer to the memory. Okay, so binary compatibility. Programs are distributed in binary form, right? So the programs will be bound to a specific instruction set. Okay, when we execute it, it depends on the architecture of the computers. So the architecture is consists of the specific instruction set. Okay, so when we write a program, it will be bound to that specific instruction format. And the instruction set is different, okay, based on the versions of the Mac, based on the processor itself. So if we have a Macintosh, you will have a different version for the instruction set. And then if you use Intel, then we will have a different version. So the new machines wants to run old program, or in this case the binaries, as well as the programs compiled to new instructions. So when we buy the computer, when we want to use a new computer, we want it to be able to run the old programs, as well as the programs that can be compiled to compile a newly compiled, okay, the new one. So for a new one, instructions is not a problem, but the old programs would lead to backward compatibility, okay, because of they need to be able to run the old program. So they need to make sure the programs that is run to the new machine will be compatible, as the instruction set evolving over time. So the selection of Intel 8086 in 1981 for the first IBM PC is a major reason that the latest PC is still using the 8086 ISA, or inside the or based on the architecture of the Pentium 4. So that's why we can still run the program from 1981 in the current version of the PC. Right. So currently all the data that we work with is in a words or 32-bit block. So remember, one register can store a word. So the load word and store word both access the memory one word at a time. So how do we represent the instructions? Remember, computer only understand 1 and 0. So when we write the or execute the MIPS command, at T0, register 0, register 0. So if we run it on the computer, it will be meaningless. So MIPS wants simplicity. So since data is in words, then instruction will be in words too. So means that within the program, okay, the instruction is inside the program, right? So within the program, we treat the program or the code as instruction in one word. Okay. So one word is 32 bits. So we would divide that instruction into fields. So each field would tell the processor something about instruction. So we can define these different fields for each of the instruction, but MIPS is based on simplicity. So they define three basic types of instruction format in MIPS. We have R format, I format, and G format. Now, what are the usage of this format? I format is used for instruction with immediates. Okay, immediates such as F is equal to G plus 10, or I plus plus. So these are immediates, constants. Okay, constants, the number with the decimal or maybe hexadecimal can be determined as the immediates. Okay, and then load word and store word. Okay, since offset is count as an immediate, and the branches. Okay, but not the shift instructions. Okay, shift instruction is under the R format. So J format is used for jump and for instruction and JAL instruction. R format is used for all other instruction. So you would be clear why the instruction have been partitioned in this way based on the field that has been determined. Right. Let's go to the R format instruction. We define the fields of the following number of the bits, the size of each field. Okay, so this is the size of each field. 655556. Okay, so for simplicity, each field has a name. Okay, so the opcode is 6 bit, RS is 5 bit, RT is 5 bit. Okay, this is 5 bit, 5 bit. Shift amount is 5 bit, and then function is 6 bit together with the opcode. So when you add it together, you will get 32 bit. It is important that on this slide and in books, each field is viewed as a 6-bit unsigned integer, not as part of a 32-bit integer. The consequence is that 5-bit fields can represent any number from 0 to 31, while 6-bit field can represent any number from 0 to 63. Okay, so what do these field integer values would tell us? Okay, for this opcode 6-bit and then function 6-bit, okay, opcode is partially specifies what instruction it is. Note that for R format, the number for opcode would be 0. Okay, for all R format instruction. Whereas for the function, combined with the opcode for R format, it will combine with the all 0, okay, 0 in opcode, and then combine with the function, okay, there's a number, there's a value, okay, not all 0. So this number would exactly specifies the instruction. So you might be wondering why are the opcode and function is not combined into a single 12-bit field. Okay, we will answer this question later on. Okay, and then we have more fields, which is RS. RS consists of source register, generally used to specify register containing first operand. Okay, so first operand or source 1. Okay, next is the target register or RT. Okay, generally used to specify register containing second operand. Note that the name is sometimes misleading. But for R format, RT become source 2. Okay, so the first one is, the first source is RS. The second is RT. So in this case, if we want to add between two content, okay, two source of registers, so you would need RS and RT, okay, with the value inside of it. And then RD is the destination register, generally used to specify register which will receive the result of the computation, like the destination or the output of where you want to store the result of the computation. Okay, notes about the register field is that each register field is exactly 5 bits. Okay, so which means that it can specify any unsigned integer in the range of 0 to 31. Why is it 0 to 31? 5 bits means that 2 power of 5 bits, you will get a 32 combination, okay, of numbers. Okay, so starting from 0 until 31, which is 11111, like that. So that's why the size, okay, the total number of registers that we have is also 32, because they are using the binary numbers to represent each of these register. Okay, so if there's sometimes you will ask, why is it not 31 or why is it not 33? Okay, so for 31, you would still needed 2 power of 5 bits. Okay, 5 bits to get the combination. And then, but you still have 1 plus 1 extra bits. Okay, that is not used. Whereas for the 33, you require 2 power of 6 combination of number to represent that register number, and also, okay, an extra 31 combination, which is a waste on the architecture. Okay, so that's why they prefer to use the base 2 number to create or to design the architecture of the assembly language. Right? So the word generally was used because there are exceptions that we will see later on. Okay, for example, multiplication and division have nothing important in the RD field since the destination register are high and low. So this you would learn using the multiplication and division, multiply and division during the lab session. Okay, the command of MFHI and MFLOW, which is move from high, move from high, and then move from low, have nothing important in the RS and RT field since the source is determined by the instruction. So you can refer this on the MIP screen sheet. And then lastly, the field shift amount or shum is contains the amount a shift instruction will shift by. So in this case, since the shift amount is 5 bit, so the command or the shift command, okay, can be shifted. Okay, the bit can be shifted, okay, by more within from 0 to 31 bit. So for all other arithmetic instruction, okay, they will set it as 0. But if the command or instruction is the shift instruction, then there will be value on this field shift amount. Okay, so this also can be seen in the MIP screen sheet. Now, before we want to learn about the MIP instruction and then the decoding into the machine language, okay, I will teach you how you want to use the MIP screen sheet. Okay, so you would need to download it, okay, on uLearn, okay, from week 6. Okay, so from week 6, um, so you will need to use it to do some decoding. Here week 6. Okay, so find the MIP screen sheet here and then try to download it. And then now, so this is the MIP screen sheet. Okay, or I can also call it as MIPS reference data. Okay, so it contains the name, mnemonic, format, and operation. Also, the value inside the opcode or the function in hexadecimal. Okay, so for example, we have ADD, register 8, register 9, and register 10. Okay, so this is an R format. So for R format, okay, you would refer to the bottom one here, basic instruction format. Okay, if it's R format, how do you want to know if the add command is an R format? So find the command under the mnemonic column. Okay, under the mnemonic column, we found that ADD here is under R format. This one. Okay. So ADD is under R format. So since it is R format, it needs opcode RS, RT, RD, shift amount, and then also function. Okay. So the operation would be, we would add content inside the register RS, content inside the register RT will be added and then stored inside the RD. Okay, so look at the value. Okay, opcode is the first column. Okay, for the first column for this value 0, and then function is 22 hex. Okay, remember this is in hexadecimal number. So when you want to put it inside um the field, okay, we determine first. Okay, R format contain opcode and function. So opcode is 0, and then function is 20 hex. So opcode here is 0, function is 32 in decimal. This is in decimal. Okay, but for me, I would prefer to use the hexadecimal, but I would write it 20 hex. Okay, so to tell myself this is in hexadecimal number, whereas the others, you don't need to put a base 10 there, because if you don't write it in hex, it means this is a decimal number. Okay, so you can use calculator, or you can use the second pages of the MAP screen sheet here to find the equivalent value of 20 hex. So look at this table of opcode base conversion ASCII symbol. Okay, the decimal. Okay, and we have binary, decimal, and hexadecimal. So remember, we want to find the decimal for 20 hex. So here, 20 hex is value equivalent to 32 decimal. So here we will write 32 decimal, or maybe you can use the 20 hex, because this later on you will need to convert to binary. But you need to know how to convert, okay, from hexa to decimal and decimal to hexa, okay. So and then for the RD is based on the position of each of the syntax. Based on the syntax, this is RD, this is RS, this is RT. Okay, because when we do the command add register 8, register 9, register 10, it is equivalent to F is equal to G plus H. So we can say this is H, this is G, this is F. Okay, which is register 8 is equal to register 9 plus register 10. So we can say 9 here is the RS. You will write it 9. 10 here is 10. And then 8 here is RD8. Okay, so some of the command in MIPS use the number of that register itself. But sometimes they would use ADD dollar S0, dollar T0, dollar T1. So if you want to know, okay, this is name, because there is no number. Because, sorry, there is a name and number here. So it means that it refers to the mnemonic. Okay, the name of that register. So look at this green sheet and then go to the first page. At the bottom, there is a register name, number, okay, and then use call convention. Okay. And then it has a name. Okay, if I write it as 0, it's here. Okay, so S0, and then T0, T1, okay, S0, S7. So to represent in numbers in binary, so you need to know the number of the register. So T0 until T7 is number 8 until 15, and then S0 until S7 is 16 until 23. T8 to T9 is 24 until 25. So most of the codings or the commands, instructions in assembly language would use this variable, this register. Okay, for storing the temporary value or save temporaries. Okay, so we can still use this T and S. Alright, so now because the 8, 9, 10 is the number itself, we can just copy the number here. Okay, remove the dollar. So you can put RD is 8, RS is 9, and then RT is 10. Okay, what about the shift amount? This is not a shift instruction. This is an add. So the value of the shift amount will be 0. Now, Okay, once we have determined the value, we put it inside the field. Okay, this is opcode R S R T R D shift amount and then function. Okay, function. Okay, so when we put a value, then we need to translate into binary. Okay, it must be in a binary number per field representation. So remember the size of each field. Opcode contain 6 bit, RS contain 5 bit, 5 bit, 5 bit, shift amount also 5 bit, function is 6 bit. Okay, so the opcode here is 0. So we will get 6 bit 0. Okay, 6 bit 0. And then 9 is actually 1001. But the size is 5. So you can add 0 at the front. And then RT is 10. 1010. And then we add 1 at the front. Add 0 at the front. Okay, and then for the destination, okay, register 8 here. Okay, so when we convert it, it becomes 01000. Okay, so the RD is also 5 bits. Shift amount is also 5 bits. But remember, since this is not a shift, so the value will be 0. So we would add 5 bit 0 on the shift amount field. Okay, for the function, remember it is 32 in decimal or 20 hex. So this will come as useful for you. The hex, okay, the first digit would be convert into 4 bit here, and then the first digit, the second digit would be convert into 2 bits of binary numbers because the size of the functions is only 6 bit, not 8 bit. Okay, so 2 can be represented, 20 hex can be represented with 100000. Now, what do we need to do after that is that divide each of these combination into 4 bit. Okay, 000 we got 0, and then 0001 is 1, 0010 is 2, and then 1010 is A. Okay, this is 10, so the representation is A, and then 0100 is 4, this is 0, this is 2, and then this is 0. So when we combine it, okay, you will get like this, and then you will write hex. And then the decimal representation is combination or the conversion from hexadecimal to the decimal. So command, this command or this representation is what we call as the machine language instruction. So easy, right? If you know how to use the MIP screen sheet. Okay, so what about iFormat? iFormat use immediates. Okay, use immediates means constant. Okay, for example, something like f is equal to g plus 10. Okay, so 10 here is the immediate. Okay, so immediate can be constant number, can be offset, okay, for the load word, store word. Okay, so the 5-bit field only represents number up to the value 31. So immediates may be much larger than this because sometimes you want to do some operation, you would need the immediates. Okay, so ideally MIPS would have only one instruction format for simplicity. Unfortunately, we need to compromise. Okay, so they define new instruction format that is partially consistent with the R format. First, notice that if instruction has immediate, then it would use at most 2 registers. Remember, this is a constant. F is equal to G plus 10 this is a constant. Okay, and then GF is as $0 and then G is as $1. So this is the registers that we would use for the I format. So in this case, only 2 registers at most will be used. Okay, now inside the immediate field, because this is a constant, right? Constant number or offset number. Okay, so the for example, the comma ADDI, SLTI, SLTIU, SLTIU. So the immediate field is sign extended to 32 bits. Thus, it's treated as a sign integer. Okay, for example, okay, for a number 1000000000 and then 00000000. So this is 16 bit of the immediates. Okay, and then okay, since add IU, okay, add I anything that has a I here means that they are operating the immediate as a numbers constant. Okay, so they treat it, okay, as the sign, as a sign. So the most significant bit on the left side here would be the sign of that number. So if it's a 0 means positive, if it's 1 it will be negative number. So when we want to operate or execute, the immediate field would be sign extend to 32 bit based on the sign bit 0 here. So they would add 16 bit 0. Okay, 16 bit 0 to be added with another registers that contain that number. Okay, so let's say S0 ADDI S dollar S0 comma dollar S1 comma 10. Okay, so if it's like this, okay, the content inside the S1 will be the source 1. Okay, so the source 1, which is in 32-bit number. Whereas the 10 here is immediate with the size of 16-bit. Okay, so 32-bit plus 16 may not look uniform or simple. Okay, so it will be not good if there is some um, sign there that needs to be added. So that's why they need to sign extend it. So now if they sign extend, okay, if the sign is 1 here, 1 0 0 0 0 0 0 0 0 0 and then 0101. Okay, to tell this is a negative number. So when they sign extend, they would extend it based on the sign bit here. Okay, so 11111111 like that. Okay, so 16 bit can be used to represent immediate up to 2 power of 16 different values. So this is large enough to handle the offset in a typical load word and store word. Okay, plus a vast majority of values that will be used in the set less than immediate instruction. Okay, so we will see that what happen if the number is too big in our next slide. Okay, now let's do the decoding of the I format into a machine language. We have ADDI $21, $22, and then -50. So the opcode is for ADDI. Okay, look for ADDI and then you search. Okay, you will search inside this MIPS reference data. So search ADDI. Okay, so this is ADDI, which is an I format. The opcode value is 8. Okay, it's 8. So here opcode will be 8, and then this is RT, RS, and then immediate. So how do I know that? I will go down and then look at the basic instruction format here. It has opcode RS, RT, immediate. Okay, so RS is the source. Okay, the register that contain the source value. Okay, so this is a register containing the operand, whereas RT is 21. Okay, so we just remove the dollar. So this will become a target register, or where we would store the result of the computation. And then the immediate is the second source, okay, with a constant number. Okay, it can be decimal or hexadecimal. To represent the decimal, you just need to put the number itself. But to represent the hexadecimal, you will write 0x at the front. And then when I write 10 means that 10 base 16. Okay. So by default, the immediate is in decimal. Okay. So MIPS instruction, for example, ADDI $21.22 and then -50. Okay. So we know that this is opcode, and then opcode RT, destination or target, RS, and then this is immediate. So you can fill in the I format field. This is immediate. And then this is opcode. Okay, so opcode must be on the most significant bit on the left side. And then this is RS, and then this is RT. Okay, so if it's a negative number, then it will be sign extend. Okay, sign extend here until enough 16 bit. After that, when they do some operation, then they will sign extend again to 32 bits. Okay, and then the rest you can just use the calculator or use the MIP screen sheet here. Okay, 21 decimal. Okay, 21 decimal is this. Okay, so value is 10101. Then 22 is 10110. Like that. Okay, so we would fill in the 5 bit for the register, 6 bit for the opcode. Okay, opcode is 8. Then we can convert it into binary. Okay, so the unsigned. Okay, although the command written U is an unsigned, but actually it is a signed extent. Okay, it is signed extent because during the execution, the immediate is only the size of 16 bit, but when they do operation, they must be in uniform size. So if it's 32 bit word, then the operation must be in 32 bits. Okay, 32 bits. So they would automatically sign extend in the immediates to 32 bits. Okay, so that's why we call the unsigned command is a signed extended integer. Okay, the rationale is that the add IU, okay, add immediate unsigned, can be used to add without overflow. Okay, without overflow. Okay, SLTIU would suffer because we want to have an easy hardware design. So does this mean we will get the wrong answers? No. It means that the assembler has to handle any unsigned immediates, okay, which is the range from 2 power of 15 until 2 power of 16. Example, with a 1 in the 15th bit and zeros in the upper 2 byte, as it does for numbers that are too large. Okay, so there is some problem with this sign extend immediate. Okay, the chances are that ADDI, load word store word, and SLTI will use immediates small enough to fit in the immediate field. But what if it's too big? Okay, so it needs more than 16 bits. Okay, so we need to find a way to deal with the 32-bit immediate in any I format instruction. Alright, so let's say if the immediate is too big. Okay, immediate is too big, then you want to store this into a register. So we need to find a way to deal with the 32-bit immediate in any I format instruction. The way to solve it is by using the software and new instruction. Okay, so don't change the current instruction. Instead of we add a new instruction to help out. The new instruction is the load upper immediate and then the register number with the dollar and then put an immediate. So this stands for LUI stands for load upper immediate. Okay, they would take 16-bit immediate and put this bit in the upper half. Okay, so remember when we put an immediate a constant 10, right? 10 in binary is 1010 and then 1 2 3 4 1 2 3 4 1 2 3 4 like that. Okay, so the um, F is equal to G plus H, which is ADDI, register 8, register 9, and then 10. Okay, so this is the immediate. They would you need to sign extend into 32-bit. Okay, 32-bit 1 2 3 4. Okay, 1 2 3 4 1 2 3 4. Okay, another 4-bit. Okay, now so this is 32-bit. Once they would sign extend, okay, then we have a complete or full 32-bit data. Okay, but when you add I or immediate, anything that has a constant there, it only occupy on the lower half, okay, lower half of the data, okay, or the space. So here is the lower half. This is the higher order half. Okay, high order half. Okay, the problem is that the high order half is there is no command. Okay, there is no command to load the high order half of the binary set. So instead of they introduce a new instruction which they call load upper immediate. Okay, load upper immediate. It takes 16-bit immediate and puts these bits in the upper half of high order half of the specified register. So in this case, for example, um, load upper immediate register as 0 and then 61. So this can be convert, okay, or encode as the value of 61 will be loaded on the high order half. Okay, high order half. What about the lower order half? Okay, since we can only load 16-bit of data, then the lower half would become all 0. Okay. Now, how does the load upper immediate help us? It copies 16-bit constant to left 16 bits of the 32-bit register. Here, it means that it will copy the constant to the left 16-bit of the 32-bit registers. In this case, high order side. Okay, so then we will use the OR immediate to combine 16-bit high bits and 16 low bits into a giant 32-bit number. For example, we want to add 0x ABAB CDCD, okay, and then add the content together inside the T0 and then store back into T0. Okay, so we know that immediate only can access 16-bit, right? So when they want to execute, only the CDCD can be written um, in the register. Okay, so now for this command, we need to put load upper immediate. LUI $80, 0x ABAB. So they divide it into 4 hexadecimal number. So ABAB using a load upper immediate means that the upper half here, okay, upper half here will be filled with AB, AB. And then or immediate AT, AT means that the source come from here, okay, from the previous line. So the first source is AT, the second source is the constant. So in this case, CD, CD. Okay, so because we are using the previous register to or immediate the value, then the upper 16 bit is not touched, okay, but the lower 16 bit will have value, okay. So in this case, we can see the first half and then the second half has been fulfilled, okay. So then use ORI to combine 16 high bits and 16 low bits into a giant 32-bit number. Okay, so another I format is the branches. Branches for branches like BEQ and BNE, okay, they use I format. But in this case, what is the immediate? Okay, what is the immediate? They are using the same thing, okay, but the immediate here, okay, specifies only 16 bits of data number. And then the program counter has byte address of the current instruction being executed. Okay, so note that we point the 32-bit pointer, 32-bit pointer to the memory. So immediate cannot specify entire address to branch to. Okay, because the size is, the immediate is only 16 bit. Okay, so then the storing of that address must require the load upper immediate. Okay, now how do we usually use branches? Okay, in C++, you learn about if, else, while, for. Okay, so this is branches in assembly language. So loops are generally small, typically up to 50 instructions. Function calls and unconditional jumps are done using jump instruction, J and JAL. Okay, not the branches. So in conclusion, you may want to branch to anywhere in memory, but a branch often changes PC by a small amount. Right. The solution to the branches in the 32-bit instruction is by using PC relative addressing. So let 16-bit immediate field to be signed, choose complement integer to be added to the PC if we take the branch. Note, instructions are word, so they are word aligned. Okay, so instruction is in the 32-bit size, okay, whereby they occupy the 4 cells of byte, 1 byte, 1 byte, 1 byte. Okay, so since the byte address is always a multiple by 4, okay, so 4 in binary is 100, so that's why it ends with a 00 in binary. So the numbers of bytes to add to the PC will always be a multiple of 4. So we will specify the immediate in words. Okay, so this is a sample of MIPS code whereby you would loop the command, okay, until certain condition is met. Here, the content inside register 9 and then compare to register 0. If it's true, the content is the same, then they would jump to N, meaning they would exit from the loop. Okay, so this is on the line 1. Okay, and then we have ADD $8, $8, register 10. Okay, and then ADDI $9, $9, -1. After the statement, okay, let's say BEQ, the content here is not the same to 0. Okay, so the content here is not the same to the 0. Then we would exit this loop. Okay, so but if it's the same equal to 0, sorry. If it's not equal to 0, sorry. If it's equal to 0, then we will exit the loop. But if it's not equal, then we execute the next instruction. So if condition not met, then branch is not taken. Okay. So after the instruction, we would jump. Okay. We would jump the loop back again and run the command until the condition is met. Okay. Then we can branch to exit the loop. Okay. So the BEQ branch is an I format. Look at the MIPS. Okay. Uh, Branch here. Okay, branch. BEQ is 4 hex. 4 hex. So opcode is 4 hex. And then RS is 9. Okay, RS is 9. RT is 0. Okay. So BEQ here is BEQ $9 $0. Okay, END. You can represent this as opcode RS RT. Okay, it will be different, a little bit different. This is RS, this is RT, and then this is the immediate. Okay, now, so the opcode RS RT is easy. Okay, for the first operand, second operand is easy. But what about immediate? The immediate is in words. END, right? Okay, now, how to determine the number? So we align each of the line. Okay, we put a number. Okay, we count it. Okay, for line 1, which the branch command. Okay, the branch instruction. So this is line 1. And then the next one is, it will be line 2, line 3, line 4, line 5, right? Okay, so to count the offset of the immediate field. Okay, so it means that you need to count how many instructions to jump to that label. You want to jump to the end here. Okay, so you will need to count, okay, how many lines you want to jump. So the counting here does not start at 1. Okay, so the usage is based on Mars, whereby, okay, the next line is count as 0. And then the next one will be 1. And then this is 2. And then this is 3. Okay. So, the number of instructions to add or subtract from the PC, starting at the instruction of this BEQ, okay, would be PC is equal to PC plus PC plus 4 plus, okay, immediate or count times 4. Okay, count times 4. So here, count is equal to 0. And count is equal to 1, 2, 3. So here means that 3 times 4 is equal to 12. 12 plus 4 is 16. Like that. Okay. So the count here is the immediate. The count here is the immediate. So your immediate size will be 3. Okay, will be 3. So in this case, your decimal representation. Okay, let me correct this part. Okay. So 490, 4 is for the opcode. So we represent into 000, 100, and then 9 is 01001. 0, register 0 is all 0. For 3 here is 16 bit. So we can represent as 011. Okay, 011, 0000 until enough 16 bit that you can get. Okay, you may count this like this. Okay, put a space there, 0011. Then you will get a 16 bit of representation. Okay, so for branches, we assume that we won't want to branch too far. Okay, so we can specify the change in PC. Oh, before I forgot. Okay, the counting here, okay, going down will be the increment of the count. But let's say you want to branch at the top, okay, before this branch. Okay, let's say you want to go to L1. L1 is here. So how many steps that we need to jump to the top? Okay, you need to negative the number. Okay, you negative one, negative nine, negative one. Okay, negative one like that. It's because of the PC is currently running, going down. Okay, the PC or the program counter. Okay, they will point to the next line, next line, next line. So the next line is this one, this one, this one. But let's say you want to branch or jump to the previous line. Okay, previous line. Then you need to subtract. Okay, so this would depends. Okay, this would depends on the number of the count itself. Okay, so the immediate can be a negative number. It can be a negative number. So you need to do some 2's complement. So negative 3 must be changed into a 2's complement. You can use the calculator to get the 2's complement for this number. Okay. Now, after the branch, okay, so the branch can be assumed that we can just jump or branching to not too far, a few lines, okay. So we can just specify that changes in the program counter. But for general jump like J and JAL, we may jump to anywhere in the memory. Hence, what we call as the pseudo direct addressing. Because we want to jump anywhere, so we use the pseudo direct addressing. Ideally, we could specify a 32-bit memory address to jump to. Unfortunately, we can't fit both a 6-bit opcode and a 32-bit address, which would mean 32 plus, the address is in the 32 bits, right? So, and then we add 6, it will become 38, okay, which would not, it doesn't fit into a single 32-bit word. So, we need to compromise the value of the address. So, for J format, it only have two field, opcode 6-bit. Okay, this is 6-bit. Target address is 26-bit. Okay, so the key concept is that we want to keep the opcode field identical to R format and I format for consistency. So the important field is the opcode here. Okay, and then the rest will be a little bit different compared to the I format and then R format. Okay, and then we will combine all other fields on the R format and the I format to make room for large target address. So in pseudo direct addressing, the effective address is calculated by taking the upper 4 bits of the program counter. And then we concatenated or combined to the 26-bit immediate value target address, and the lower 2 bits, okay, will be added or concatenate with the, we combine with the 00. So for now, we can specify 26-bit of the 32-bit address. You may want to ask why is it a 00? Okay, note that when the jump happened, it is in the word align address. So one word is equivalent to 4 byte. Okay, so because 4 is represented as 100, so when we jump, okay, we add 4, 4, 4, 4. So that's why the 00 here is concatenate with the target address. Okay, now how to specify 28 bits of a 32-bit address? Okay, so where do we get the other 4 bits? The 4 bits is the 4 highest order bits from the PC. So since the upper 4 bits of the PC are used, this constrains the jump target to anywhere within the current 256 megabyte block code. Okay, so means that the coding must not exceed, okay, then 256 megabyte block of code. Okay, or 1/16 of the total 4 gigabyte address space. If we absolutely need to specify a 32-bit address to jump anywhere within the 4 gigabyte, then we can always put it in the register and use the JR command instead of we use a jump command. Okay, if you use a JR, the content inside the register, you can put an address there so that they can jump to that to that address that is stored inside that register. Okay, so let's find where does each part come from. Okay, now the loop or the if we want to jump loop here, okay, look at the command. Okay, there's some command and then dot 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 dot. Okay, then we have a jump loop. Okay, so the loop is located on this address. Okay, so the PC would run based on the memory address of that instruction, right? So the loop command here, okay, the loop label is positioned on this memory address. So 0040024, okay, we change or transform it into binary. Okay, when you transform or reverse the value, okay, find the representation in binary, you will get a 32-bit of binary numbers, and then find the loop target address from the bits 27 until here 2. Okay, so this is 31 until 28, and then this is 27 until 2 here. Okay, and then we copy this to become a 26-bit target address. You would store it here. Okay, you will store it here. And then the opcode for jump is this. Jump, okay, is 2 hex. Okay, 2 hex. Now, 2 hex means that 00010. Okay, because it is a 6-bit, right? Okay, so this is the binary representation of the J format. Okay, so how do they read back? They would take out this. Okay, they would take out the target address, and then okay, find the new PC. Okay, find the new the PC bits, 4 bits of the PC. Okay, for example, the PC is 00 here, is 0 here, this one. Okay, so it's 000. So what happened is that they would, okay, they will put a 000 of the 4 bits of the PC. Okay, and then we add a 00 at the back. Okay, you will add a 00 at the back. Okay, and then the rest would be the 26-bit of the target address. Now you will get a 32-bit. Okay, 32 bits of address of where to jump. Okay, where to jump. Okay, so here it will jump to here. Okay, so in summary, okay, I have explained about the RING, and then the branches use a PC relative addressing, jump use absolute addressing, and then this assembly is simple and start by decoding the opcode. Okay, so you need to refer to the MIPS screen sheet. For example, given an assembly language statement in this machine instruction. Okay, using this machine instruction, actually this is an assembly language statement, and then you need to know what is the assembly language statement based on this machine instruction. The first step is that you convert the hex to binary to find the op field. So we set the bit based on the R format field because that is the longest or the most field that we have in the all format. So we have 31 until 28, and then 20, 21, 22, 28, 28, 29, 30, 29, 30, 31, 32. Oh, okay. It should be 27 here. Okay. No, sorry. Should be, yeah. It should be 26. 26. 31 until 26 here. Okay, will be the opcode. So when you convert the hexadecimal here, 000 here, Okay, you will get 0, 0, 0, 0, 0, 0, and then you divide it into 6 field. Okay, 6 field of R format. Okay, for the opcode, you will get 0, 0, 0, and then for the function, you will get 1, 0, 0, 0, 0. So when you look like this, you will know, oh, okay, opcode is 0, and then there's a value for the function. Okay, so this is R format. Okay, this is an R format. So you can convert the function value into hexadecimal. 10 is 2. 0, 0, 0 is 0. So this is 20 hex for this field. Okay. So you can start to look at the uh, um, MIPS here. Okay. Function opcode is 0. Function is 20 hex, right? So that is add. Okay, add command. Okay, and then you can decode the rest by following the R format. Okay, depends on the format that you can determine. If the first 6 bit has a value, then it is not an R format. It can become I format or J format. Okay, so the key is on the opcode field here. Okay, if it's a 0, then you can just divide it to become an R format. So this will become RS, RT, RD, shift amount, and then function. Then convert it. Okay, now you have the value 101 is 5. So what is 5? Okay, look at the number on the register. 4. We have 4 until 7 means that A0 is 4, A1 is 5. So here, this is A1. And then 1111 is 15. So we look at this. Okay, 15 is T7. So $T7. And then 1000, which is 16, is S0. Okay, S0. Okay, shift amount is 0, and then this is add. Okay, after that, you will rearrange the values into an assembly instruction. Okay, because this is an R format, so add will be added at the front. And then this is RD, this is RD, and then RS, RT, like that. Okay, so that's how you want to decode your machine language. Right, so that's all for me. Thank you.